our building. I will book a classroom and we will have a test. And my idea is the following, that there will be 5 questions, 5 tasks. And if you do one task correctly, you will get the grade 3.0. Okay, 2 tasks correctly, 3.5, and so on and so on. Okay, so 1 out of 5 to pass the exam, the test. Okay, do you see it on my piece of paper?
Could you repeat when the test is going to be held?
One task correctly out of 5, grade 3.0. 2 tasks correctly, 3.5. 3 tasks correctly, 4.0, and so on and so on. Okay. I think it's fair deal.
Will these tasks come from tutorials, or there will be general lectures, or what kind of task will they be?
It will be both from tutorials and from the lectures, but I will tell you about questions in the end of the semester of our lectures.
Okay, thank you.
It will be something similar to what is going on the lecture or on the tutorials. Some of the questions may be the same as something we have done on the lecture or on the tutorials. Okay, so maybe we'll prove some theorem. So maybe one of these tasks will be prove something, and this is the same as something on the lecture or on the tutorials. Okay, so and there are activity points. Maybe this word points is not the best word, but activity. So if you do some tasks on the tutorials, it can upgrade your grade plus to the grade. Okay, so for example, you have done 3 tasks correctly on the test, and you had some pluses for activity, then you will get 4 plus half, 4.5. Okay. I think it's a fair deal. Are you with me?
Yes,
Yes.
that's okay.
Okay, so you know everything about the test, what is needed now, and I will upload the notes before the next lecture. Okay, so let's start with the lecture. And so on the previous lecture, we have talked about languages and grammars and Turing machines and other machines. So from now on, we'll talk mostly about, for some time, Turing machines and recursive and recursively enumerable languages. Okay, so I need to prepare something more before we discuss these topics. So one couple of more introductory things. Okay, so now from now on we will fix the alphabet to 0, 1. So we have a binary alphabet, and the languages, we will consider the languages over this alphabet. Okay, so we have a Turing machine. We know that we can imagine the Turing machine as some kind of machine with a tape and with a head moving along the tape and with a finite control. And now we want to encode such a Turing machine into a binary sequence. Okay, so we have our Turing machine M. It has n states, Q1 up to Qn. The alphabet is 0, 1, binary, the input alphabet. The tape alphabet consists of 0, 1 and the blank symbol. This is the transition function. Let's assume that Q1 is the initial state, B is the blank symbol, and let's assume that we have only one accepting state, Q2. Okay, for convenience, we will use variables. X1 is equal to 0 to make the rest of the encoding easier to understand and easier to write. X2 is 1 and X3 is B. So our tape alphabet symbols are X1, X2, and X3. And we set K1 to L and K2 to R. Yes, so this the head can move to the left or to the right, K1, K2. Okay, so how to encode our Turing machine M? We will encode the moves of M. That means we will encode the transition function. Okay, so suppose that the value of our transition function for the arguments qi and xj is equal to qk x m and kl. That means if the head, if the finite control is in the state qi and the head observes the symbol xj, then it changes the state into qk, writes xm on the tape and moves either L or R depending on KL. Okay, so this value of the transition function will be encoded into 0 to the power of I. This is I. So I zeros. Then 1. Then 0 to the power of j. So j zeros. 1. K zeros. 1. M zeros. 1.
Ponieważ są to bardzo wymagające grzyby.
Okay, so the number of zeros means the index of these variables, and ones separate the zeros. Okay, so this is the code of just one move, and what is the code of the whole M? The code of M is the following. We start with 3 ones. Then there is code 1. Code 1 is the code of the first move. We put all the moves of M in some order, any order, and this is the code of the first move in this order. Then we separate it from another code with 2 ones. 1 1, code 2. This is the code of the second move, another move. 1 1, code 3, 1 1, and so on and so on. 1 1, code. For example, there are R moves of M, and the code ends with 3 ones. Okay, so 3 ones in the beginning and in the end, and codes of the moves separated with 2 ones. This is the code of M, where code 1 up to code R are the codes of all moves of M. Okay, so maybe let's see an example. I will write one Turing machine, and I will encode this Turing machine. So M has 3 states. Yeah, this is fixed. This is fixed. Okay, and now I will write the values of the transition function. It will be a partial function. So M will have only 4 moves. Q of delta of Q1 and 1 is equal to Q3 0 R. Delta of Q3 0 is equal to Q1 1 R. Q31 is equal to Q2 0 R. And the value of Q3 and the blank symbol is equal to Q3 1 L. Okay, so the code of M is the following. We start with 3 ones, then the code of the first. So this is 1 0 for this Q1 1. 1 is x2, so now we have 2 zeros. That means 1 1. Q3, so 3 zeros. 1 0. We have denoted 0 with x1, so this is 1 0. And we have denoted R with K2, so 2 zeros. Okay, so this is the first move of M. We separate it with 2 ones, and now I will write the move of the second, the second move of M. So Q3, so 3 zeros, 1 0, so 1 0 1 1 0 1 1 is x2, so 2 zeros, 1 R is K2, so 2 zeros, 1. Okay. So this is the end of this second move. So 2 ones, and now here is the third move. 0 0 0 1 0 0 1 0 0 1 0 1, 0, 0. This is the end of the third move. And maybe I will write the last move here. 0, 0, 0, 1. B is x3, so 3 zeros. 0, 0, 0, because we have q3 here. 1 is x2, so 0, 0. And L is k1, so 0. So this is the end of the fourth move. And we finish with 3 ones. Okay. So this is the whole code of our M. This is from the example. Okay, so of course this encoding is not one-to-one, because for example we can change the order of moves, and the same Turing machine will have a different code. So this encoding is not one-to-one. This is not a function. Yeah, because one Turing machine can have many codes. For example, the moves of our Turing machine in different order. And one code corresponds to at most one Turing machine. Okay, so from now on, we will use sometimes these codes of Turing machine, and I will denote by M with this kind of brackets a code of M, a Turing machine M. We know that a Turing machine can have many codes, so this is any code of M. Okay, and often we will use a pair of a string consisting of a pair of strings denoted by MW. So this string consists. This is a concatenation of the code of M and some string W. Okay, and I will write the following remark. Okay, so if we have encoded our Turing machine into some code, then okay, so we have our Turing machine and we know what is a language accepted or recognized by this Turing machine. So we assume, so if you have some string and it is a correct string of a Turing machine, for example, it starts with 3 ones and there are codes separated with 2 ones and ends with 3 ones, then it is a correct Turing machine and it accepts some language. So we assume that if a string is not a correct Turing machine, for example, it doesn't start with 3 ones. So we assume that this is a code of a, let's say, a broken Turing machine. That this Turing machine does not accept any word, any string. So we assume that if some string which we consider as a code of a Turing machine is not a correct code, of a Turing machine, then the language of this machine is empty. Yeah, so from now on, we will consider any string as a code of a Turing machine, but only some of them are correct Turing machines and they accept non-empty language. All the others are accepting empty language. Okay, so this is the encoding of Turing machine. Now we will need some order in the set of strings over a binary alphabet. I don't have focus, maybe in a moment. Okay, so we will use an order which is called canonical order.
Sorry, we can't see what you wrote.
Now?
No, it's okay.
Okay. So we want to have a linear order in the set of all strings over 0, 1. So we sort them by length, and 0 is smaller than 1. So
Sorry,
this is
it's
the order.
lost again.
Okay, I can see it now. Maybe it's better. Okay, so we want to have a linear order in the set of all strings, and we sort them by length. Shorter words are smaller than longer, and 0 is smaller than 1. So the first string in the order is the empty string, then 0, 1. 0, 0, then all the words, the strings of length 2. 0, 0, 0, 1, 1, 0, 1, 1. Then all the strings of length 3. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, and so on and so on. Now all the strings of length 4, and so on and so on. So this is the canonical order, and we will use this order often. Okay, so we know that every Turing machine can be represented, maybe I will write easily represented, for example, by this encoding from the previous page, by a string finite string. Maybe I will write from over the binary alphabet. So of course, this set is countable. This set is countable, so the set of Turing machines is also countable. So there are only countable many Turing machines. This is a very important observations. Okay, and we will also need the following thing. We want to generate all pairs of natural numbers. How to generate all pairs ij where I and j are some natural numbers. So we can do it in the following way. We know that there are the set of such pairs is countable. So I will draw a table. The rows of this table are indexed with I and columns with j. This is 0, 0, 1, 2, 3, and so on. 1, 2, 3, and so on. So we can generate them in the following way, in the following order. We start from here, and we do it like this. And so on and so on. So I will enumerate some of them. So the first one is 0, 0. Then we'll have 0, 1. Then 1, 0. Then 0, 2. 1, 1. And 2, 0. So this is the only pair with the sum 0. Next, there are 2 pairs with sum 1. Next, there are 3 pairs with sum of elements 2. Then we will have 4 pairs with sum of elements 3. 1, 2, 2, 1, 3, 0, and so on and so on. Next would be 5 pairs with sum of elements 4, and so on and so on. So in this way, we can enumerate all such pairs, and we know that every such pair is somewhere in this sequence. Okay, so now we are ready to discuss the languages. Okay, so I recall that we have denoted with all is the set of all languages over, now we fix the alphabet, over 0, 1. R is the set of recursive languages
Excuse me, we cannot
Yeah.
see what you're writing. Thanks.
and RE is the set of recursively enumerable Okay, and we know that every language from RE is recognized by some Turing machine, and we know that every language from R is recognized by some Turing machine with stop property. Okay, so if we have some language, then of course by L with this hat, we denote the complement of this language. So all the strings all the strings which not belong to L. Okay, so we have the following theorem. First theorem. If language L is recursive, then the complement is also recursive. Okay, let's see the proof. Okay, so L is recursive, so there is a Turing machine with stop property which recognizes this language. So Turing machine with stop property recognizing. I will denote it with M. So this is M. So the language of M is L. And now I will construct the Turing machine with stop property that recognizes the complement of L. Maybe I should write M here. Okay, so we just have to switch this outputs. Yeah, so this is M. And our Turing machine M, the complement is the following. Okay, so M prime, no, M complement runs M on the input string, and if M answers yes, then it answers no. And if M answers no, it answers yes. So it is easy to see that, of course, this machine accepts all the strings that are not accepted by M and none other strings. And this is a Turing machine with stop property because it halts on every input. Okay, so we have proven the theorem. Okay, and we define another class of languages. It is called Core. this is the set of all languages such that their complements are recursively enumerable. So Core is this class of complements of recursively enumerable languages. So what we know now is that R is a subset of RE, and it is of course a subset of all, and the same inclusions with Core. It follows from this theorem. Okay, so let's check the cardinalities of these sets. So of course, all this is the set of all strings over 1, 2. So of course it is uncountable. We know that every language, every recursively enumerable language is accepted by some Turing machine, and we have observed that there are only countable many Turing machines. So there are only countably many recursively enumerable languages, and of course, the cardinality of this set is the same as the cardinality of Core. So of course, these inclusions are proper because there are more languages here than here, and there are more languages here than here. So we know from these simple observations that these inclusions are proper. Our goal is to show that these inclusions are also proper. And we will show it in a moment. Okay, so we have proven that the class of recursive languages is closed under the operation of complement. So we have done something that that we wanted to do on the tutorials, but there are more of such tasks to show. So we one down. Okay, so let's prove another theorem. Maybe I will get another piece of paper. Okay, I will start writing, and then we'll get the focus. Next theorem. So if L is recursively enumerable, and also its complement is recursively enumerable, then this language is recursive. Okay, so we will write a lot of proofs in this way as the previous one. So I will draw some small Turing machines, and then I will construct bigger Turing machines using the smaller ones as some kind of bricks. Okay, so since L is recursively enumerable, there exists a Turing machine. I will denote it with M1, recognizing L. Turing machine M1, recognizing L. And it looks like this. M1, input string, and it answers yes. Okay, since the complement of L is also recursively enumerable, there exists a Turing machine M2 recognizing this language. Okay, and now I will construct, using these two Turing machines, I will construct a Turing machine with stop property that recognizes L. I will call it M. Okay. Okay, so this is M. On the input string W, it runs both M1 and M2 on W. Since every string belongs either to L or to the complement of L, one of the Turing machine will give us answer yes. If M1 answers yes, then it means that W belongs to L. M answers yes. If M2 answers yes, then that means that W belongs to the complement of L, so it doesn't belong to L, so M answers no. In both cases, one of these Turing machines answers, so this Turing machine M always answers. So this is a Turing machine with stop property. Okay, so this proves that L belongs to R. Okay, so from these theorems we have proven we can get the following corollary. I will also denote it with theorem. I will call it theorem, but this is just a summary of what we have done. So let us consider some language over the binary alphabet. So we know that one of the following conditions holds. One of the following conditions holds. The first condition. Both L and its complement are recursive. Okay. The second condition is that one of these languages, one of these two languages is recursively enumerable but not recursive. Because we know that if one of them is recursive, then the other one is also recursive. So one of them is recursively enumerable but not recursive, and the other one is not recursively enumerable. because we know from the previous theorem that if both of them are recursively enumerable, that in fact they are recursive. And the last option is that none of them is recursively enumerable. Okay, so I can draw the situation on the picture, and the picture looks like this. This is the set of all languages. This is the set of recursively enumerable languages, and this is the set of their complements. And here is the set of recursive languages. And what we want to do now is we want to put some languages on this map. Here we want to put some, so we know that here we have all the regular languages, context-free languages, and so on. We want to put some languages here. And this is our next goal. So now I will discuss some languages. Usually it will be a pair. We will discuss pair of languages. Some language L and its complement. So I will start with, maybe I will separate it with a language called diagonal language. Okay, I will start writing and then you get the focus. Okay, so I will, in a moment, I will draw a table similar to the table with which we use to enumerate all the pairs of natural numbers. What will be in this table? So in the rows will be strings, and we will see them as the input strings. Strings from over the binary alphabet in canonical order. And we will see them as the input strings. And in the columns of the table will be also strings. The same sequence of strings. But now we will see them as these strings. We will see them as codes of Turing machines. Okay, so this is the table. Okay, so the rows are indexed with input strings, the columns are indexed with Turing machines, and I will denote the entries of this table with A's. A1, A12, A13, A21, A22, A23, and so on. And this table is a binary table, so every aij is 0 or 1, and we'll define it in this way. Aij is 1 if the input string wi is accepted by the Turing machine MJ. And it is 0 otherwise. Okay, so for example, if we consider the input string wi and the Turing machine MJ, then MJ is a sequence. Maybe it is a sequence of a correct Turing machine, maybe not. If it is not a sequence of correct Turing machine, then then we assume that this Turing machine does not accept any word, any string, so this entry will be 0. And in case that MJ is a code of a correct Turing machine, we can run this Turing machine on the input string wi and check if it belongs to the language or not. If it belongs, then this entry will be 1, otherwise it will be 0. Okay, so we have a table of 0 and 1s, and what we look at this defining this language is the diagonal. So we are interested in this. So now we define the diagonal language. Okay, we will call this language LD, D like diagonal. This is the set of all input strings wi such that aii is 0. So in other words, that is the set of the input strings such that this input string is not accepted by the if Turing machine. Okay, so let's observe that this language is not empty. Why? Because, for example, because the empty language is recognized by some Turing machine. For example, if the code of this Turing machine is not a correct code. And if, so we know that in this case, the language accepted by this Turing machine is empty. So it does not contain any string. In particular, it does not contain the string wk. So wk belongs to LD. Okay, for example, M2, this is the second string in the canonical order, so this is only 0, a string of length 1, 0. So this is not a correct code of a Turing machine. So the language of M2 is empty. So W2 does not belong to this language, so W2 belongs to the diagonal language. Okay, so we have defined the diagonal language, and now we will prove that this language is not recursively enumerable theorem. Okay, so suppose so every Turing machine is somewhere in this sequence. Yes, somewhere in this sequence. So if some Turing machine accepts the diagonal language, this Turing machine is in somewhere in this sequence. So it is MK for some K. So suppose that Turing machine MK recognizes the diagonal language. So in other words, the language of MK is LD. So now let's consider the string, the input string WK. WK belongs to the diagonal language by the definition if and only if, maybe I will write it in this way, if and only if AKK is 0. Or in other words, WK is not accepted by MK, by the definition of the diagonal language. But L of MK is LD. So we have proven that WK belongs to the diagonal language if and only if it doesn't belong to the diagonal language. So of course this is a contradiction. I will denote the contradiction. Contra. So that means that this assumption was false. So the diagonal language is not recursively enumerable. Okay, so we will see some more languages, and then in the end, I will put them on this map I have shown you before. Okay, so the next language is called universal language. Maybe I will. Okay. Universal language. Okay, we will denote the universal language by LU, you like universal, and this is the definition. This is the set of all strings which are of the form MW. I recall that this means that this is a string consisting. This is the concatenation of a string consisting of the code of M and W. Of course, any string we can consider any string such as such concatenation. So this is the.
Excuse me, what's W here?
W is an input string. This is just any string, but we can consider the string as consisting of two parts. The first part is the code of a Turing machine, and the second one is input string for this Turing machine. And such string belongs to LU if and only if M accepts W. Yeah, so in this language, the strings are codes of a Turing machine and concatenated with input string, and we can encode this code of Turing machine into a Turing machine, run this Turing machine on the input string, and see if it accepts or not. Okay, so the next theorem is that this language is recursively enumerable. Okay, so I told you before on the previous lecture that we will use three methods of showing something on Turing machines. One of them is to define formally define the transition function. And it is a very formal method, but maybe less intuitive. The second way is by these pictures, using smaller Turing machines to construct bigger ones. And the third method will be by description with words. So now I will use the third method. So I will describe a Turing machine accepting this language. Proof. We will construct a Turing machine MU, U like universal, and this Turing machine that we will construct is called the universal Turing machine. And this machine MU will recognize the universal language. So I will use a model of Turing machine which has three types. We know that if we consider only the set of languages accepted by Turing machines, that this model is equivalent to the basic one. Yes, so I will construct a three-type Turing machine, but that means that there exists a basic model of Turing machine that accepts the same language. MU has three types. Maybe on the first type, our Turing machine will store the input string. So our universal machine gets the input string MW on the first state, and it will stay there. On the second, this MU will work on the second tape and the third tape. In the second tape, MU will simulate the computation of the Turing machine M on the input string W. Okay. And on the last tape, so here, this tape, the second tape, is the same as would have the Turing machine M on running on W, and so this will be tape of M. And in the third tape, MU will store the current state of M. Yeah. So MU will simulate the computation of M on W, and it uses the second tape as the tape of M and the third tape as the control of M. Okay, so now I will describe the computation of MU.
I'm sorry, I have a question. And how does it distinguish when, where the Turing machine ends and the word starts in the input string?
It can check all possibilities. Yeah, because this is a finite string. So this MU can divide the string into two parts in any place.
Okay, thanks.
If one of these options is accepted, then this string is accepted. Okay, so I will write it in points. First point, check if the input string is correct. Here is a partial answer to your questions. So check if some prefix of the input string is a correct code of a Turing machine. The other way to solve this problem is to use a non-deterministic Turing machine. So if we use a non-deterministic Turing machine, then in the first step, it will randomly, maybe not randomly, it will divide the input string into two parts. Yeah, so each, so we have a non-deterministic choice here, the partition of the input string into two strings, and if if for any non-deterministic choice the answer is yes, then the whole then MU accepts. But we can also check all possibilities with deterministic Turing machine. Okay, so if the input string is correct, so of course, if it is not a correct code of a Turing machine, for example, the input string does not start with 3 ones, because we know that the correct code of a Turing machine starts with 3 ones. Then, of course, the answer is no, because this is not a correct Turing machine, so it does not accept any string. It does not accept W. So if it is not a correct input string, then the answer is no. And now we consider the case where it is a correct input string. Then maybe MU checks. Then MU writes W on the second tape. So it prepares on the second tape and third tape, it prepares the simulation of M on W. And the code of the start state of M on the first tape. Okay, now it will simulate the computation of M on W. If there is a code of an accepting state of M on the third tape, that means that M accepts W, then MU stops. The computation and accepts the input string. If not, it has to perform another move of M. So otherwise, MU finds the code of the move of M from, so on the second tape we have the tape of M, on the third tape we have the state of M. So MU finds on the first tape where there are stored all the codes of moves of M, the move from the configuration described on the second and the third tape from the configuration. Of M described by the third tape, the state of M, and the second tape. So it is symbol observed by the head. Okay, so it searches for the value of the transition function on the first tape, and then it performs this move on the second and the third tape. So it writes a symbol and moves the head. And on the third tape. So it changes the state according to the value of transition function. Okay, and goes to the third point. So checks if the state on the third tape is up. So we have a loop here. This 3 and 4 is a loop. It performs a move of M, checks if the state on the third tape is accepting. If yes, then accepts. If not, then performs another move, and so on and so on. Okay, so basically MU divides the input string into M and W, and then runs M on W and accepts if M accepts W. So this universal Turing machine can simulate any computation of any Turing machine. So that's why it is called the universal Turing machine. Okay. So maybe to sum up this construction, I will write that the input string for MU is accepted, so it belongs to the universal language, if and only if W belongs to the language of M, so it is accepted by M. So this is the definition of the universal language. And now we will show that this language, I don't know if I managed to, maybe I will start from the top. We will show that the universal language is not recursive. Okay, so suppose that it is recursive. Then there exists some Turing machine with stock property that accepts this language. Let's denote it with M. Okay. We will show that the complement of the diagonal language is recursive. This will be a contradiction because we have shown that this diagonal language is not recursively enumerable. So if this language is recursive, then also its complement, so the diagonal language is recursive, and this is not true because we know that LD is not even recursively enumerable. Okay, so this is a contradiction. Then this is a contradiction because we know that this language is not even recursively enumerable. Okay, so now I will prove that under this assumption, the complement of diagonal language is recursive. How? We will construct a Turing machine with stop property. I will call it M prime that accepts the complement of the diagonal language. Okay, so now I will describe this M prime. Let W be the input string. Okay, so since it is a string over 0, 1, that means that it is somewhere in the canonical order. So of course, there exists an algorithm so a Turing machine with stop property that computes the index of W in the canonical order. This, for example, this algorithm enumerates all the input, all the strings in the canonical order, and for each string compares it with W. Yeah, so of course this algorithm will eventually find the index of W in the canonical order. So so the first thing that M prime does is uses this algorithm to find the index of W. So we will use this sentence in some more proofs. So that means that M prime runs the algorithm for searching the index of a string in the canonical order. Okay, so it turns out that, for example, it is K. I will denote this index with K. Yeah, so the first thing that M prime does is finds this K. And now consider the string mk. Okay, so this is wk, it is w, so we have this string, and this is the same string. So this is the string ww, in fact. Then m prime runs our Turing machine from this assumption m on this string. Okay, so let's see what's going on. So the string mkwk is accepted by m if and only if the language of m is the universal language. If and only if mkwk belongs to the universal language. And we know by the definition of the universal language, this is if and only if mk accepts wk. And by the definition of the diagonal language, that means that we have 1 on the diagonal in the k place. So akk is equal to 1. So that means that wk does not belong to the universal language. Okay, so we have this Turing machine m prime. First, it uses algorithm, so Turing machine with stop property. Then it simulates m, and m is also a Turing machine with stop property. So m prime always holds on every input, so it is a Turing machine with stop property, because both this algorithm and m have the stop property. So so this is a contradiction, because we have constructed an algorithm recognizing the complement of diagonal language. Hence, we know that this assumption was false, so universal language is not recursive. Oh, maybe I forgot to tell you that this diagonal trick used in this definition of the diagonal language is not something unique. This diagonal method is often used in logic. So this is a well-known method, diagonal. Okay, so we know that this language is not recursive. And okay, so maybe let's write another theorem. The complement of the diagonal language is recursive. Proof. Let W be the input string. And we will construct the Turing machine. that accepts this language. Okay, so I will describe how M works. First, like in the previous proof, first M computes the index of W in the canonical order. Let's assume that this index is K again. So W is equal to WK. Then M runs MU, the universal Turing machine, on the input string MKWK. Yeah, so this is WW. Okay, so if MU accepts, then that means that W belongs to language of MK. That means on the diagonal, in the kth entry of the diagonal of this table, we have 1. That means that this string does not belong to the diagonal language, so it belongs to the complement. Yeah, maybe I will write it again. So that means that they belong to this input string belongs to the universal language. That means that MK accepts WK. That means that WK does not belong to the diagonal language, so it belongs to the complement. Okay, so let me find this map, because here it is. So now we know that in this map, I will draw this map later, maybe bigger one. So we know that here somewhere is LU. Maybe I will show you now just, and then later I will draw the map. So we know that the universal language is somewhere here. It is recursively enumerable, but not recursive. So the complement of LU is somewhere here. And we know that the complement of the diagonal language is recursive, but not is recursively enumerable, but not recursive. So it is also somewhere here. So its complement, so the diagonal language, is somewhere here. So we know 2 languages from here. Now the universal language and the complement of diagonal language, and 2 languages from here, the complement of the universal language and the diagonal language. Okay, and we will place also 4 more languages here on the map. So maybe I will start writing and then we will get the focus. Okay, So the next part of languages, it will be called LNE. It is the set of set of codes of Turing machines that accepts non-empty language. So this NE stands for non-empty. And the second one is LE. E is for empty. So this is the set of codes of Turing machines accepting the empty language. So of course they complement each other. So we want to place these two languages on our map. So the first theorem is that the language non-empty, LNE, is recursively enumerable. Okay, so we construct the Turing machine. I will call this Turing machine MNE. With the same letters as the language, such that the language accepted by this Turing machine is our language. Okay, so for the input string M, our Turing machine simulates for every pair of natural numbers the computation of M on the string Wj, j is the first number from the pair, for k moves. If M accepts, then our machine accepts the input. Okay, let's discuss it for a moment. So we know that there exists an algorithm that enumerates all these pairs. First, it will enumerate, so it will generate 0, 0, then 0, 1, 1, 0, 0, 2, 1, 1, 2, 0, 0, 3, 1, 2, 2, 1, 3, 0, and so on and so on. So for it, so our Turing machine generates these pairs, and for each pair, it simulates, it runs this Turing machine M on the input string. So it generates the pair JK. Then it generates the J word in canonical order. So for every JK, it generates the WJ, and then it runs M on WJ for K moves. So suppose that this Turing machine accepts some string. So of course this string is somewhere in the canonical order. So let's denote the index of this string W. So suppose M accepts some string W. This W is somewhere in the canonical order, so let the index of W be J. So W is Wj for some J. And if M accepts this word, then it accepts it after the computation lasting for some number of moves. So let's denote this number of moves by K. So we know that M accepts Wj after K moves. So eventually, our Turing machine generates this J and K, and will simulate M on Wj for K moves. So M will accept, and we know that M accepts some string, the string Wj. So it accepts any string, so the language of M is not empty. So that's why M and E accepts M. Okay? Are you with me? I don't know.
Yes.
Okay. Okay, so I will continue. We have place here. It's a space. Okay, so we know that this language is recursively enumerable, and now we will show that the complement, so LE, is not recursive. And this is an error because I should start it from on the next page because I want manage to. Yeah, let's start from the top. Okay, so once more, the theorem is the following.
Sorry, the angle is wrong. You can't see what you are writing.
Now,
Nope. That's okay.
okay. Okay, so this will be not a full proof. The next, I think, three proofs or two proofs will be sketches with one detail omitted. I will discuss it in a moment. So let's start this proof by stating that there exists an algorithm A. Algorithm means that there exists a Turing machine with stop property A that for a given input string MW constructs a code of a Turing machine. I will call this Turing machine M prime, such that the language accepted by M prime is either empty if W is not accepted by M, or full, so every string belongs to the language, if M accepts W. So now I will draw this M prime Turing machine. Okay, so this is M prime. It ignores completely the input, runs M on W. If M accepts, then M prime also accepts. So never mind the X. If W is accepted by M, then M prime accepts. So it accepts every input. If M does not accept W, then M prime does not accept. So then it accepts the empty language. So this is the M prime Turing machine. And now back to the proof. So suppose there exists a Turing machine with stop property, so the algorithm, an algorithm I will call it ME, E like empty, that accepts this language. Then we will construct an algorithm B such that B accepts the universal language. This will be a contradiction because we know that the universal language is not recursive. So there exists no algorithm, no Turing machine with stop property accepting value. Okay, so now I will draw this B. Okay, so this is B. So on the input, MW, it runs the algorithm A described above. So the algorithm A returns the code of Turing machine M prime here. And now B runs ME on this M prime. And if ME accepts, then B rejects. If ME rejects, then B accepts. Okay, So let's see what's going on. So the input string is accepted by B if and only if ME rejects the input. So if and only if M prime, the code of M prime is rejected by ME. That means that this language is LE. So the code of M prime is not in LE. That means that the language of M prime is not empty. So there are only two options by the definition of M prime. Either L of M prime is empty or the set of all strings. So if it is not empty, then it means that it is the set of all strings. Maybe I will write that. And this is the case by the definition of M prime when M accepts W. And this is, of course, the case. So if M accepts W, that means that the pair MW belongs to the universal language. So we have shown that MW belongs to the language of B if and only if it belongs to the universal language. So the language of B is the universal language. So we have constructed a Turing machine with stop property for recognizing the universal language, and this is a contradiction because LU is not recursive. Contradiction. So we know that this assumption is not true, so LE is not recursive. Okay, so we have shown how M prime works. We have shown how B works, but the one detail is omitted from the proof. We have not constructed A. Yeah, so this algorithm that constructs the code of M prime, because it is not hard, but it is maybe hard to write, not hard to understand, and a lot of details. Okay, so one detail is omitted from the proof, how the algorithm A works. Okay, so we know this, and now we will prove that the complement, so L and E, is also not recursive. This is very easy because we know already that that if this language is recursive, then its complement is also recursive. And we have just proven that it is not. Okay, and the last theorem about this pair of languages is that LE is not recursively enumerated. Again, this is a very easy proof because we know all the facts needed to prove this theorem, suppose that this language is recursively enumerable. Okay, since its complement is recursive, and we know that if it's recursively enumerable, and we know that if the language and its complement is recursively enumerable, then in fact it is recursive, we get the contradiction. So we have, since both LE and its complement are recursively enumerable, we have that this language is recursive by the theorem from the beginning of the lecture. And this is a contradiction because we have shown that it is not recursive. So this language is not recursively enumerable. Okay, so we can place these two languages on our map. Let me find the map. Oh, here it is. So L non-empty is somewhere here, and L empty is somewhere here. I will, after discussing the last pair of languages, I will draw a bigger map and place the languages on the map. Okay. So the last pair of languages. The first one is LR, and it is the set of codes of Turing machines such that the language of this Turing machine is recursive. And its complement, so non-recursive, the set of codes of Turing machines accepting non-recursive languages. Of course, they are complements. Okay, again, I won't manage to write the proof here, so I will use another piece of paper. Okay, so these are the last two languages we want to put on our map. So we need to show where they are on the map. So first we'll prove that LR is not recursively enumerable. Okay, proof is the next two proofs are similar to the previous one. So first we observe that there exists an algorithm that for a given input string MW constructs a code of Turing machine, I will denote by n prime, such that the language of n prime, so it is similar to the previous one, is either empty, and this is when W is not accepted by M, or it is the universal language if M accepts W. And again, I will draw this M prime and another machines, but we will omit the construction of A. So we won't see how A works. But you can imagine how it works, but we won't write it. Okay, so let me draw this M prime machine. Okay, so our M prime takes the input X, and it is first it runs M on W. If M accepts, then it starts the simulation of MU on the universal machine on X. And if it accepts, then M prime also accepts. So if M does not accept W, then MU doesn't even start. So M prime does not accept, so it does not accept X, any X, so it accepts the empty language. And if M accepts W, then M prime accepts its input if and only if MU accepts this input. So if and only if this input belongs to the universal language. So this is it. Okay, so now back to the proof. So suppose there exists a Turing machine, I will call it MR, recognizing the language LR. Then we will construct a Turing machine B recognizing the complement of the universal language. This is a contradiction because we know that the complement of the universal language is not recursively enumerable. And so I will draw now this Turing machine B. Okay, so B for the input MW runs A, and A returns the code of Turing machine M prime, and then B runs MR on this code of Turing machine M prime and accepts if and only if MR accepts. So let's see what's going on. So the input string is accepted by B if and only if MR accepts the input. By the definition of, so if and only if the code of M prime is in the language LR, because the language of MR is LR. And by the definition of LR, that means that the language accepted by M prime is recursive. We know that the language of M prime is either DMT language or the universal language. Since the universal language is not recursive, that means that the language of M prime is empty. And this option holds when M does not belong to, where M does not accept W, by the definition of the language of M prime. And by the definition of the universal language, that means that the pair MW does not belong to LU, so it belongs to the complement. So we have shown that MW is accepted by B if and only if it belongs to the complement of the universal language. So the language of B is the complement of the universal language. So this is a contradiction because we know that this language is not recursively enumerable. So this assumption was false. So this language is not recursively enumerable. Okay, and the last proof for today is the fact that its complement is also not recursively enumerable. Again, the proof will be similar. So first observe that there exists an algorithm A that for a given input string MW constructs a code of Turing machine I will denote it again by M prime, such that the language of M prime is either the set of all strings if M accepts W, and L the universal language otherwise, if W does not belong to the language of M. Okay, so again, we won't describe the details of A. So we know that such algorithm exists. We can imagine how it looks like, how it works, but we want to write it down. We will just use it. But I will draw this M prime Turing machine. So here is M. W. Yes. MU, universal machine. Yes. Okay, so on the input X, our Turing machine M prime, first it runs W on M on W, and if M accepts, then M prime also accepts. So if M accepts W, then M prime accepts any string. So in this case, M prime accepts all strings. But there is also option for acceptance if W is not accepted by M this way. So if M does not accept W, then M prime accepts if and only if MU accepts. So if and only if X belongs to the language of MU, so the universal language LU. So this is it, correct. And now, suppose there exists, so suppose that this language is recursively enumerable, so there exists a Turing machine recognizing this language. I will call this Turing machine M and R, like the language. And now I will construct Turing machine B that accepts the complement of the universal language. So similar to the previous one, this is a contradiction because we know that this language is not recursively enumerable. So now I will draw this Turing machine B. Okay, so for the input string MW, first B runs A, and M constructs this Turing machine M prime, and then B runs our Turing machine from the assumption M and R on M prime, and it accepts if and only if M and R accepts. So again, let's see what's going on. So MW belongs to the language of LB if and only if M and R accepts the input. This language is L and R.
We can't see.
Now,
Yeah, but
okay, so this language belongs to M and R by the definition if this language, the language of this machine is not recursive. But there are only two options for this language. It is either the set of all strings, which is of course recursive, or the universal language. So the first option is unavailable because it is recursive, and we know that this language is not recursive. So it must be the second option. So L of M prime must be the universal language. And the second option holds if and only if W does not belong to the language of M. And that means that the pair MW does not belong to the universal language, so it belongs to the complement. So we have shown that MW belongs to the language of B if and only if it belongs to the complement of the universal language. So the language of B is the complement of universal language, and this is a contradiction because this language is not recursively enumerated. Hence, this assumption was false. Okay, so I will finish the lecture with this picture, and maybe I will use the previous paper. So here will be the picture. So now to see the next page first. Okay, so the picture is the following, maybe bigger one. This is the set of all languages over the binary alphabet. This is the set of recursively enumerable. And this is the set of co-re. So we have shown that LU belongs here and the complement belongs here. LD belongs here, the diagonal language, and the complement belongs here. We know that LE belongs here and the complement, so LNE belongs here. And we have shown two languages that are not recursively enumerable. So both of them lie somewhere here. Here will be LR and here will be LR. Okay, so we have shown that there are languages that are recursively enumerable and not recursive. So we know that these inclusions are proper. And the same here with core. Do you see the picture? Okay, I will make photos of these notes and upload them and send them to our group. Okay. Are you with me?
Yeah.
Yeah.
Okay, so now let's have a 5 minutes break and we'll have the tutorials. So in this break, I will write as posts the tasks from the homework. And if you want to present the solution, then please volunteer as an answer to my posts, okay? So in a moment, I will write the tasks as posts.
Okay.
And if you want to present the solution, then it will be as so write that you are ready, and I will choose one of you, and then this chosen person will send the solution as an answer. Okay, so let's have 5 or 10 minutes. How do you? How long the break should be? 5 minutes, 10 minutes?
10.
Now it's 1:30, so